Where were we? We hence proved from this equation R equals to rho L square upon V that R is directly proportional to L square when rho and V are constant. So this is the thing that examiner asked from me. We have to reach this formula first of all by using this concept that V volume is equals to cross sectional area into length of the conductor. The first formula was related to the electrodynamic chapter. R equals to rho L upon A. I substituted A by V upon L. My formula became rho L square upon V. And you can see that my if I change increase my resistance, my length of my conductor will also increase. Then there is a direct relation between them. And what is the most compulsory thing here? That rho and V must be constant. Rho is constant here. Why? Because it is material dependent. We are using only one material, and volume is constant. He has already told you that volume is constant. So such kind of questions may come that you might have not studied during the lecture. So that is basically related to your how much you have gone into the depth of the topic. So let us discuss about the part C now. Is this part B is clear? Anything that you want to ask?
And I understood.
Okay, in part C, he has given the circuit. And what he is saying. Read the question.
It's asking that you battery electromotive
Suppose see the
force
circuit.
and
What kind of circuit is this? This a battery of EMF and internal resistor R is connected to a variable resistor of resistance R.
okay.
Okay, so now there is an ammeter that is connected in series and voltmeter that is connected across the resistor, this variable resistor R. And you can see that it is an internal resistor, small r, and there is a flow of current that is I in my circuit. So that is a very simple circuit given here. And what is now given here? In figure 5.2, what he has given, the graph of voltage against current, you can see that it is a straight line.
Okay.
Graph of voltage against current. Now what it is he is asking. Figure 5. Use figure 5.2 to state the EMF E of the battery. I want to state the EMF of battery by only saying the figure. Can you tell me what will be the EMF of the battery by just
EMF of the battery.
yes, by looking this graph? Anything you remember the thing we have discussed?
I think so. We find like the how do you say it? Like the gradient type.
No, no, no. Come here. Come to the circuit. See here.
Okay.
We have internal resistor in my battery. Okay. So if I want to know the EMF of my battery, if I make my current value 0, so that means there will be no loss of voltage against this resistor R and this resistor R. Means my total voltage in my circuit will be the total EMF of my battery. So whenever there is a current 0 in my circuit, I can calculate my EMF of the battery by just simply connecting a voltmeter across it. So if you take a battery and connect a voltmeter across it, the voltmeter will tell you the EMF of the battery. It is very simple. When circuit is not complete, you can calculate the EMF by just simply connecting a voltmeter across the battery. So when the current is 0 in my circuit, the voltage that is shown by my voltmeter is basically the EMF of battery. Is it clear? So 2.1,
Yeah.
2.2, 2.3, 2.4. So 2.4 volt is my basically the voltage of EMF of my battery, not my voltage of battery. My voltage of battery will be different when the current value is not 0. We will discuss this thing in the next parts. In part 2,
Okay.
use figure 5.2 to determine the power dissipated in the variable resistor when there is a current of 5 ampere. Okay. So he is asking that when there is a 5 ampere in my circuit, if the current in my circuit is 5 ampere, what will be the power dissipated in my variable resistor?
So first we'll write the power formula. Yeah, P is equal to,
There are three different formula: P equals to VI, P equals to I square R, P equals to
first
V square
VI
upon.
will take, because
So there are multiple formulas, but we will choose on the data given here. So we are given with the current in the circuit. So come here, we are given with the current. Now the current value is not zero, it is 5 ampere. So there will be some potential drop across this resistor R. So what he is asking to calculate the power dissipated in the variable resistor, means the power that is dissipated by this resistor. So if I want to know the power that is dissipated by this resistor, I know current in my circuit. Since this resistor, variable resistor R is connected in series with the small internal resistor R, that means the value of current that will be passing through this resistor R, capital R, will be 5 ampere. So I know the current value, but I don't know the resistance value. So I cannot use the formula I square R. I cannot use the formula uh, I square R, I cannot use that. And V square upon R, can I use that formula? It depends upon the scenario. You can use that. And the third formula was VI. So if I am able to calculate the voltage across my variable resistor, so I can easily use the formula VI to calculate the power. Yes or no? I know
yes.
the current value, but I don't know the voltage value. So how will I calculate the voltage value? Okay, so we have plotted
Uh,
a graph of V against I. This V is basically across the value of voltmeter. The voltmeter measure the potential difference is V. See here. So what is the current value? 5 ampere. When the current is 5 ampere, 5 ampere will be in middle of these here. 1, 2, 3, 4, 5. There will be 5 ampere here. So when there is a ammeter is showing me 5 ampere. This ammeter is showing me 5 ampere. This voltmeter is showing me what reading? So I can calculate through my graph. I can see here. When my ammeter is showing me 5 ampere, I plotted a graph and I can see that the voltmeter reading will be 1.1, 1.2, 1.3 volt. So my voltmeter reading is 1.3 volt. So can I use this formula? Voltage across the variable resistor R is 1.3 and the current is 5. Multiplying these two values will give me power across the variable resistor. What was voltage? 1.3. What was current? 5 ampere. So 5.3 into, sorry, 1.3 into 5, 6.5 volts. Clear?
yeah.
This voltmeter readings are basically the voltages values across my variable resistor R. And this ammeter reading is giving me the current values. So what I did, I made a, if you have you doing practicals P3, you are doing the things like that. You connect ammeter and voltmeter in a circuit and you plot the values of the current and voltage. So for example, there is a 5 ampere corresponding to this voltage value is 1.3. So you consecutive plot consecutive points, and this points you will plot on the graph and will make a graph of it. So from this graph you can predict any for example voltage value on a known current value, or you can find a unknown current value on a known voltage value by using the equation of straight line. You know y equals to mx plus c.
Yes.
State what is represented by the value of gradient of the graph. What my gradient will tell me of this graph? Tell me.
Gradient of the graph, like what it will give you.
Yes. Okay, so let us discuss that. This is a straight line. Straight line is represented by y equals to mx plus c. What is on my y-axis? On my y-axis, we have voltage. Yes or no?
Yes.
Gradient, I don't know. Okay, I write it m. But on what is on x-axis? We have current. So I will write I in place of x. And what is y-intercept? Y-intercept was 2.4. And what was 2.4? EMF of my battery. Can I write in place of Y-intercept capital E?
Yes.
Okay, now I have to determine what my M is representing to me. Mi equals to the voltage minus EMF. Wait a second here.
Then
Okay, so if you remember the equation for calculating the potential difference across my battery, what was that? V equals to E minus IR. Remember that equation?
yeah.
Whenever there is an internal resistor in my battery, some of the EMF is lost due to the internal resistor. So the voltage across my battery becomes the EMF minus the potential difference across my internal resistor. So this was my equation. This equation is very much similar to this equation. I know the value of gradient will be negative here. So this thing will be negative here. My gradient is negative here. So that means if I compare this thing to this equation, what do you think? What will be my gradient? Let me write this equation like that. V equals to minus Ri plus E. So we have V here, we have V here, we have I here, we have I here, plus E plus E. What is gradient? Can you compare these two equations? What will be my gradient? Minus R. You can see here, there I have written minus R aside my current I. Compare these two equations. V equals to Mi plus E. Gradient will be equals to minus R. So this was the equation that I already know. And I can see that this equation is very much similar to this. Comparing this two equation, I will get gradient as minus R. But yes, my grade, yeah, minus R. Yes. So is this thing clear to you?
Yeah. So the gradient gives a second what?
What are you saying?
Like what will we write for the answer now?
You just simply write here that gradient is telling me minus R, or you can write minus internal resistance. So this was our last part here. So we have discussed two questions. One was related to electrodynamics and the one was related to nuclear and particle
Wait, what
physics.
do we write again?
Let me show you. Wait a second. Minus internal resistance. You can either write this or you can either write this. Okay, so we will discuss the next question in the next class.